Now it's working. Yeah. So, okay. So, well, now it goes automatic. Okay. So, consider a co-rank 1 distribution on a manifold M, and I'm sorry, something is proceeding without any my intervention. So,
Slideshow włączyłeś.
Pada?
Slideshow włączyłeś.
Co zrobiłem?
Slideshow
Nie,
włączyłeś.
a gdzie to jest?
No nie wiem, no bo jak to się samo przewija.
Ojej, no. So let's so consider the quotient of this vector bundles and the projection of the tangent to this. This is this line bundle will play a prominent role in all the contact geometry. So this hyperplane field we call the contact structure if these two forms which associates with every two vector fields belonging to C, that is taking values in C, the projection of the brackets. It is a student exercise to show that this is actually a tensor. So assuming it is non-degenerate, we get a contact structure. Of course, any hyperplane field can be locally, at least, presented as the kernel of certain non-vanishing one form. So this every such one form defining the contact structure we call a contact form. It's clear that these contact forms defining C are defined only up to conformal equivalence. Yeah, because if you multiply this by non-vanishing function, that of course the kernel remains the same. Because this two form must be non-degenerate, it has to have a even rank, therefore the dimension of the manifold itself should be odd, say 2n+1. And these contact forms are in textbook usually characterized in this sense, so that this form is of course a volume form, a top differential form, which should be non-vanishing. Okay, so we call a contact manifold trivial if we fix a global contact form such that C is presented as its kernel. And we call it trivializable or coorientable if there exists a global contact form, but it is not fixed. Of course, not all contact form manifolds are trivializable, and I will show some example in due course. So if in the literature, people sometimes work only with trivial contact manifolds, so with contact forms. And for contact forms, an important vector field defined by the structure is so-called Reeb vector field, which is uniquely determined by the conditions the contraction with the contact form gives 1, and R is in the kernel of d eta. And famous contact Darboux theorem says that there are always local coordinates around any point in which contact form takes this form. For this form, it's easy to see that the Reeb vector fields is actually d over dz. In physics literature, thermodynamics, statistical mechanics, Hamiltonian and Lagrangian mechanics, especially in studies of system with dissipation, etc., contact structures are generally co-oriented. I mean, in the literature of the subject. And this is, I'm sorry, I don't know. Okay, so the standard presentation is the following. So we start with the contact Hamiltonian understood as a function on the contact manifold and define the associated contact Hamiltonian vector fields as the unique vector field XCH satisfying these equations. The definition in this presentation is actually ad hoc definition, so this is not clear why we should define contact Hamiltonian vector fields in this way. Second, this definition strongly depends on the choice of the contact form. So even if we choose a contact form in the same conformal class, we get completely different Hamiltonian vector field. This is because, of course, the RIP vector field depends strongly on the choice of the contact form in the conformal class. So in Darboux coordinates, this contact Hamiltonian vector fields takes this form. So just to your knowledge. Now, some obvious concepts from contact geometry. So first, contactomorphism, clearly diffeomorphism of manifolds which preserve the contact structure. So they map this distribution C1 into C2. If we use contact forms as defining locally contact structure, then this contactomorphism preserves only the conformal class of the contact form. So it preserves the contact form only up to a non-vanishing factor. Now this shows that so even people who deal exclusively with co-oriented contact structure use this definition, which is non-consequence in a sense. So this are contactomorphisms. So of course, contact vector fields are vector fields whose local flows are local contactomorphisms, which in terms of the Lie bracket or Lie derivative can be expressed in this sense. So contact vector fields differentiate vectors belonging to the contact distribution to vectors belonging to the contact distribution. That's clear. Let me introduce now some notations. For a vector bundle, I will denote this L cross a vector bundle with the removed zero section. So the set, the open submanifold of non-zero vectors in this vector bundle. In particular, R cross is R without zeros, which is canonically the multiplicative group. And one nice observation in this, in rank 1 case, is that for line bundles, so rank 1 vector bundles, there is one-to-one correspondence between line bundles and principal R cross bundles. This is one way is quite easy, namely you have a line bundle, you just remove the zero section. So of course there is an obvious free action of non-zero reals by multiplication on this. So this is a principal bundle. And the other way, so with a principal R cross bundle, I associate a line bundle, which is actually the line bundle associated with this principal bundle and standard representation of R cross on R by multiplication. Now, let me mention the following very important observation in if this relation of contact geometry with symplectic geometry is concerned. Namely, if I have a non-vanishing one form, eta, then one very nice characterization of the fact that this one form is contact is the fact that the principal bundle, which is the line bundle generated by this one form, which is of course line subbundle in T star M with removed zero section, is a symplectic submanifold of the cotangent bundle with its canonical symplectic form. We have to remove the zero section because of course the zero section is a Lagrangian submanifold in T star M, so there is no chance that any subbundle containing zero section is symplectic submanifold. Again, this principal bundle generated by eta clearly depends only on the conformal class of eta, yeah? Because this is just a line bundle spanned by this one form. Now consider this line bundle, this line subbundle in T star M is of course canonically trivial. So this trivialization is explicitly given by this eta. So we can parameterize this line, this principal bundle actually with this Cartesian product of R cross times M, which is of course a trivial R cross principal bundle. So to Sx we associate eta at x multiplied by S. Of course, this is a diffeomorphism. If we pull back the canonical symplectic form on this cotangent bundle to R cross M, then this is of course the differential of the pullback of the Liouville one form, and we obtain this two form on this object. From what I said before, it follows that this form is symplectic if and only if eta is contact. So this is a nice characterization of contact form in symplectic terms. This is very important if you consider, for example, contact structures in supergeometry, because of course the standard definition with the help of the volume form is not working, because of course there are no top forms of top even forms on supermanifold. So starting with this contact form eta, we obtain a symplectic structure on this trivial R cross bundle, which is the standard symplectization of co-oriented this should be contact manifold. To generalize it, notice that any contact distribution is locally defined by means of the contact form. So an immediate corollary of this observation is that the Courant distribution is contact if and only if, so this C0, CO maybe better to say, is the annihilator of this C, so this is a line bundle in the cotangent bundle with the removed zero section. In terms of this line bundle we started with, this is the dual of this line bundle with the zero section removed. So this should be a symplectic submanifold in the cotangent bundle, with the symplectic form being the restriction of the canonical one. So locally, if eta locally determines C on a certain neighborhood U in M, then of course this principal bundle is locally trivial, and our symplectic form is exactly as before. I mean, this is the presentation. So this is the very general symplectization of contact manifolds. So this is certain principal R-cross symplectic subbundle in the cotangent bundle. Of course, if C is not, so this principal bundle is generally not trivializable. This differs the general case from the trivial one. Another observation which we will use later is that canonical symplectic form on the cotangent bundle is linear. This is the differential of linear form, which is the Liouville form. So it is linear, means it is homogeneous of degree 1. So homogeneous with respect to the action of multiplication by non-zero reals. Nabla here is the Euler vector field in the cotangent bundle. So this linearity should be also expressed as the fact that the Lie derivative with respect to nabla of omega is omega. Now, I want to propose a geometric abstraction of these constructions of symplectization. So I will call a symplectic R-cross bundle this object, which consists of principal R-cross bundle P over M with the projection tau, with an action denoted with H. So to every non-zero S and non-zero real number S, I have something like multiplication by S of elements of points of P. And this principal bundle is equipped additionally with a symplectic form, which is one homogeneous in the sense that the pullback of every HS of omega is S omega. So this is exactly geometric abstraction of this model we noticed before. This symplectic R-cross bundle, so they do not form clearly a category, but at least we can easily say what are isomorphisms of this symplectic R-cross bundle. They are just diffeomorphisms preserving both structures. So I mean they are R-cross equivariant symplectomorphisms. So with this abstract symplectic R-cross bundle, we can associate immediately two geometric objects. One is the Euler vector field, which is the generator of the action. I mean, this is R plus, so positive reals with multiplication, because this vector field corresponds only to this part of the action, of course, because vector fields, so this is the generator, so means this is defined on the neutral component of the group R-cross, which is exactly the group, multiplicative group of positive reals. So I will call it by analogy with the cotangent bundle also nabla. So this is the Euler vector field. And because I have this symplectic form omega, I can contract it with NAMBLA and I obtain certain non-vanishing one form, the Liouville form. So I have a full analogy with this cotangent bundle terminology. Namely, if I have a symplectic air-cross bundle, then this symplectic form is homogeneous with respect to this Euler vector field. This Liouville form is semi-basic, and omega is d theta, exactly like we have for Liouville form on the cotangent bundle. For any local trivialization of this principal bundle, which is of course a priori non-trivializable, we have the expression for this Euler vector fields is SDS, and there is a contact form eta such that our omega is exactly as the symplectic form induced by this contact form. And the Liouville form is just eta multiplied by S, which is, of course, the natural coordinate on our crest.
Excuse me. Sorry, quick question. What is semi-basic?
Okay, semi-basic means that at every point, this is a pullback of certain one form on the base. Yeah, so in this case, this is just vanishing on vertical vectors. Yeah.
Okay. Thank you.
This is very, your question is very important for this theorem, namely, which says that if I start with an abstract symplectic air-cross bundle, that this bundle induces actually a contact structure on the base manifold, which is this contact structure is obtained as the projection of the kernel of this Liouville one form. The kernel, so the Liouville one form is not invariant with respect to multiplication, but the kernel is. Yeah, so this makes sense, and this is a contact structure. And this map is an isomorphism of our abstract symplectic air-cross bundle with this canonical one, which is associated with this contact structure defined on M via P. So this is exactly the annihilator of C with the zero section removed. And this isomorphism is given exactly by associating with every point X the value of the Liouville form. Being semi-basic, this can be viewed as a covector on M, yeah? So therefore it makes sense. So in other words, there is a one-to-one correspondence between isomorphous classes of contact manifolds and isomorphous classes of symplectic air-cross bundles. So in this sense, we can simply forget the terminology of the contact manifolds and just speak all the time about homogeneous symplectic manifolds. So I mean homogeneous in the sense that there are air-cross principal bundles with homogeneous one homogeneous symplectic form. So this symplectic air principal bundle we call a symplectic cover of this contact form it defines on M. So one can ask why we should consider different symplectic covers while we have one very good, which is canonical one, namely this one. This is because it is convenient in many geometric situations to deal with this abstract concept, because we naturally observe in many cases that we deal with symplectic air-cross principal bundle not knowing explicitly the contact structure downstairs. So this is just a very, of course, up to isomorphism, there is only one symplectic cover, but there are many realizations of this symplectic cover, which is very useful. I will show you in a moment with this example. So consider first the contact structures, which is one of basic examples of contact structures, which is projectivization of cotangent bundle. So I consider a cotangent bundle, remove the zero section. So this is clearly, so this is a linear, the vectors bundle. So I have multiplication by R, but after removing the zero section, this becomes clearly an R cross bundle. This is an open submanifold in the cotangent bundle. So with this symplectic, canonical symplectic form, reduce it to this open submanifold. And because omega is linear, so of course, after this reduction, this is one homogeneous exactly in the sense we consider. So this is symplectic, this is canonically a symplectic R cross bundle. So this is, you can see it for the first side, yeah? So it represents, therefore, by our theorem, the canonical context structure on the base manifold. The base manifold is, of course, P divided by the action, which is exactly the projectivization of the cotangent bundle. So this carries canonical contact structure, and this structure, notice that the structure is non-trivializable if only the dimension of M is odd. This depends on the fact that real projective spaces are orientable or not depending on the dimension. Another example is extended cotangent bundle. This example appears very often in physics application. So we have the canonical contact structure on R. I put it star because usually this is, of course, the manifold of reals, but playing the role of the dual of R. So this is R times T star Q has a canonical contact structure, which is dz minus, and this is the Liouville, canonical Liouville form on T star Q. Its symplectic cover is T star of the trivial R cross bundle over Q, which is, of course, R cross and times this one. The symplectic form, which is one homogeneous on this, is, of course, the canonical symplectic form, and the projection from this symplectic cover to this contact manifolds is this. So this is because in this object, S and pi are coordinates which are homogeneous of degree 1. So we have to divide this pi by S to get something what is zero homogeneous. So because here we don't have any homogeneity structure. Okay, so now, because we identify contact manifolds with symplectic covers of this manifold, so if we have two symplectic covers of two compact manifolds, this picture is finally closed by observing that we have one-to-one correspondence between contactomorphism, symplectomorphism, which are air-cross equivariant, so isomorphism of this structure, covering isomorphism of contact structures, so contactomorphism. So if I start with a equivariant symplectomorphism here, it projects to a unique contactomorphism here, and vice versa. If I start with a contactomorphism here, there is exactly one equivariant symplectomorphism upstairs covering this far. And now let me present some contact symplectic dictionary. So this is a symplectic cover of certain contact manifolds. So what are contact Hamiltonians? Now, in this non-trivial picture, they are no longer functions on the contact manifold, but they must be understood because you remember this definition presented in physics papers is not independent on the choice of the contact form in its class. So in our setting, these are one homogeneous Hamiltonians of this air-cross symplectic bundle. These are exactly, these homogeneous Hamiltonians are exactly sections of this line bundle Tm over C, and you obtain the Hamilton. So section gives you a linear function on the dual, and the dual is represented exactly by the annihilator in the cotangent bundle. So this gives you a function on P. If that structure is trivial, then the correspondence is easy, namely this contact Hamiltonian, true contact Hamiltonian is homogeneous functions defined by this contact Hamiltonian defined on M. Of course, if P is not trivial, there is no way to define, to obtain this Hamiltonian out of any function downstairs. But this is, so this is exactly what is used in the physics literature. So if you start with this Hamiltonian, you obtain exactly this Hamiltonian vector fields as presented at the beginning of my talk. So how you obtain contact vector fields out of this Hamiltonian? So these are homogeneous, one homogeneous Hamiltonian, but Hamiltonians. So they define Hamiltonian vector fields on P this time. And because Hamiltonians were one homogeneous and symplectic form is one homogeneous, these vector fields are invariant with respect to the air cross action. So they are invariant, therefore they are projectable downstairs to certain vector fields on N. So this is exactly how we construct contact vector fields out of homogeneous Hamiltonians. So we construct the standard Hamiltonian vector field upstairs and project it onto the contact manifold. What about the contact Jacobi bracket? Because of course with the contact structure is also a particular example of so-called Jacobi brackets or Jacobi bundle in the terminology of Marl, but also locally algebras in the terminology of Kirillov. So contact Jacobi brackets are just Poisson brackets. So namely, if I had two sections like that corresponding to Hamiltonians H and N prime, so the contact Jacobi bracket is the section which corresponds to the standard Poisson bracket of these Hamiltonians on the symplectic manifold. And by the way, this bracket is because for sections of a line bundle, it doesn't make sense to say that there is a derivation of sections or something like that. So these are actually the bracket which, so the sigma h acts on this as by some first order differential operators, and the symbol of this first order differential operators are vector fields on M and define again this contact vector fields. Our vocabulary is further the following. So if I have a submanifold downstairs, then I can take the pullback of N with respect to the projection, which is automatically R cross subbundle of P. Now we call N co-isotropic or isotropic if and only if this pullback submanifold is co-isotropic in the symplectic sense. Similarly, N is Lagrangian if and only if this pullback is Lagrangian. So you see, we don't need to define ad hoc certain contact concept or concept in contact geometry. We can just use the standard terminology of symplectic geometry, just in the case where our symplectic structure is homogeneous. What about contact Hamilton-Jacobi equation? So I will present it on the simplest case. So again, these are obtained from standard Hamilton-Jacobi equation. So let's start with this this simple contact structure, which is given by the standard contact form on this extended cotangent bundle. We take a Hamiltonian of this cotangent bundle, and we consider a function on Q, on the base manifold. As we know, the symplectic cover is the cotangent bundle of this trivial R cross bundle. So we extend this sigma to homogeneous function on this trivial bundle. And as we know, this Hamiltonian correspond in this standard coordinates in the cotangent bundle is S times the Hamiltonian downstairs. So we have the following equation. And now you can see that if you start with classical Hamilton-Jacobi equation in the form that H composed with ds is 0, so this, of course, the ds defines certain Lagrangian submanifold in T star R cross time Q. Then this corresponds to the equation H hat composed with the first jet of sigma is 0. The first jet of sigma defines, therefore, certain Legendre submanifold in this contact manifold. So these are roughly relation between these approaches. A few words about homogeneity structures, which I will need in the following. So this is definition of a vector bundle in terms of exactly multiplication by reals. So a vector bundle is a manifold equipped with the smooth action of multiplicative monoid R, So this is multiplication by reals in a sense, which is regular. This is a certain regularity condition. But this is important that multiplication by reals in a vector bundle completely determines the vector bundle. This is very useful because we can forget about addition. So if we speak about compatibility of a vector bundle structure with any other structure, that what was very difficult in the standard approaches was the fact that compatibility of addition is difficult to express, while compatibility with multiplication by reals is easy, but enough. So, of course, what is action is clear. H1 is identity, and HT composed with HS is HTS. Of course, this is similar to R cross bundle. The difference is that for vector bundles, this is the action of the whole R monoid, while in the R cross bundle, this is only the group action. Of course, R with multiplication is not a group. And this, in general, smooth actions of R we call homogeneity structures, and they have very nice properties, but I will not speak more about this. So geometric structure is compatible with the homogeneity structure if each AT acts as morphism of this structure. This is the easiest definition of, for instance, VB groupoids, VB algebroids, and double vector bundles, for instance. Because what is compatibility of one multiplication by reals with another multiplication by reals? This is, of course, the action acts as morphism means exactly this. They commute simply. Of course, they could be both homogeneity structure, or one could be just R cross action, which express what are linear across bundles. So this is a very useful approach to the problems of compatibility of two vector bundle structures or vector bundle structures with R cross bundle structures. An important result in this direction is the fact that we can lift easily these structures from the manifold to the tangent and cotangent bundle. So if H is a multiplication by reals which determines a vector bundle or R cross bundle, then we can lift this H to the tangent bundle by taking just THT, which is obvious, yeah. On cotangent bundle is less obvious because this is not the standard dual of the action, but this we should multiply additionally by S. This is because if we don't multiply by S, this has no sense for zero. So, but if we multiply by S, this makes sense also if S is zero, which is easily seen in local coordinates. So therefore, if we leave to Tm and T star this structure, so we obtain a new vector bundle or new R cross bundle structures on Tm, T star, M, and they are automatically compatible with canonical linear structures on these vector bundles. So usually linearity in geometry can be expressed in terms of these double structures. So for instance, omega is linear if we have something like that, and contact structure is linear if the lift maps C into C.
Janusz?
Yeah?
I have a sort of naive question. So how is it? You said that there are R structures where you include zero and R cross structures where you don't include zero, right?
Yeah.
But I haven't got it. An R structure where you're allowed to multiply by zero is it stronger, or is it like or kind of R cross or R?
No. I lift structures with 0 to structures with 0. So vector bundle to vector bundle and R cross bundle to R cross bundle. So this is consistent.
Okay, yeah, sure. But now my question is different. Is R linearity, multiplication by everything, including 0, is it a lot stronger than multiplication only by non-vanishing things? Is there
So on vector bundle, this is the same, but on R principal bundle, there is this question is out of sense, yeah, because we have no 0.
Okay.
So if we reduce linear, so if we remove the 0 section from vector bundle, this is the same. But on pure R cross bundle, this doesn't make sense because we are not able to extend it by 0.
Okay, so in principle, one kind of on many occasions one would not be able to extend it.
For line bundle, yes, actually. No, but let it discuss this after I finish, okay?
Okay, thank you.
So this facelift, actually, if we use this multiplication by S, so this is this new multiplication by S in the cotangent bundle of a vector bundle. So in vector bundle, this is the variable which is homogeneous of degree 1. So these are 2 knots. So this is 2GF triple, which is just the diagram of isomorphism of double vector bundles. I will skip this because probably I don't have time, but this is one of the most important geometrical diagram in geometric mechanics. Okay, so because we know already what are linear contact structures, so I will show you some of them, and actually all of them. So if I start with the line bundle, consider T star L cross. R cross is canonically R cross bundle, so I can leave this R cross bundle structure to T star. So this is canonically R cross bundle. This has a canonical symplectic form. And this symplectic form is actually one homogeneous with respect to the lifted action. So therefore, this is a symplectic cover of certain contact manifold. This contact manifold, of course, is the base of the whole. So the set of orbits of R cross, and you can notice that this is exactly the first jet bundle of the dual of the bundle, the first jet bundle of sections of the dual bundle. So first jet bundles of line bundles carry canonical contact structures, and this contact structure are trivializable if and only if the line bundle is trivializable. So, and they are linear, as one can easily see. This is, of course, so this is the diagram for it. So this is line bundle. This is without 0 section. This is the cotangent bundle with a standard projection, and this tau projection, which is this projection, divide the quotient by the action, gives you the first jet bundle. So in one of my old papers, I proved that these are the only linear contact manifolds up to isomorphism, of course. Yeah, so these are, and compare it with the case of symplectic structures. So the only linear symplectic structures are cotangent bundle, of course, are up to isomorphism. So this shows that these first jet bundles play the same role in contact geometry as cotangent bundles in symplectic geometry. Okay, so two group actions and reductions. So if I have a symplectic cover of a contact manifold, so suppose a Lie group acts by contactomorphism on M, we know that this contactomorphism can be lifted to in equivariant symplectomorphism. So I have lifted action of the group on the symplectic cover. And with every element of the Lie algebra of G, I have this generator of the flow of contactomorphism, which is a contact vector field. And this vector field, of course, is covered by certain R-cross invariant Hamiltonian vector field. This is what I express already. Because any symplectic cover is, of course, exact symplectic manifolds, because the symplectic form is the differential of the Liouville one form. I have canonical Hamiltonian given by contraction with this Liouville one form. Therefore, I have a canonical contact moment map, but you should notice this moment map in this presentation is not a map on the contact manifold, it's the map on its symplectic cover. So this is the standard moment map for exact symplectic manifold and a group action. This group action is additionally equivariant, which means that this moment map is not only at equivariant as associated with the potential of the symplectic form, but it is also R-cross equivariant. Yeah, so I have this property. So we can try to apply a Marsden-Weinstein-Meyer reduction for this action and moment map for a weakly regular value mi of this moment map. I will assume that G is connected. Okay, of course, we have to work in the contact case. I have to modify slightly this Marsden-Weinstein-Meyer reduction. So, of course, instead of just the inverse image of me, I consider the inverse image of all products of me with non-zero real numbers. So this me cross. This, of course, consists of, no, this is just the R-cross subbundle in P generated by this submanifold, which is the standard submanifold considered in the Marsden-Weinstein reduction. Now, I want to see what is the characteristic distribution of the initial symplectic form on this submanifold. This is actually a R-cross principal subbundle. So this is, I reduce the form to this submanifold and I look at the kernel. This is just the notation. So let me recall that G-me is the stabilizer subgroup, but consider now, this is the Lie algebra of this stabilizer, but now consider the Lie algebra G mu 0, where consists of those vectors here which belong to the kernel of me. And now let this be the corresponding Lie subgroup of G. This, of course, acts on this R-cross principal subbundle. Let M mu be the projection of this to a submanifold of M. And now the contact Marsden-Weinstein-Meyer reduction is the following. So to assure regularity, I should suppose that mu is transversal. So this contact structure, so the tangents of to this submanifold at no point is contained in the contact distribution. Then this characteristic distribution is of constant rank, so it defines certain foliation which consists of orbits of exactly this Lie subgroup corresponding to G mu 0. Now, of course, a priori, we don't know that this subgroup is closed, but if this subgroup is closed and acts freely and properly, so actually, so on this, then the reduced, so this is standard symplectic reduction. So because symplectic form on this submanifold has constant rank and characteristic foliation is simple because the group acts freely and properly. So I have the reduced submanifold with the reduced symplectic form, which is of course homogeneous. So in this sense, we reduce the original symplectic L cross bundle to another symplectic cross bundle. So we do a symplectic reduction controlling also the homogeneity. So this reduces symplectic R cross bundle, of course, covers certain manifold, which turns out to be the space of orbits of this subgroup, equipped with the contact structure, which is exactly the projection of the intersection of Tm mu with the original contact distribution by the projection P, which of course is projection of this submanifold of M to the manifold of orbits of G mu 0, which is in the case when the group acts freely and properly, a surjective submersion. Okay, so maybe just one remark. So the question whether this subgroup is close or not is close related to prequantization, because if G is compact and connected, then this subgroup is closed if and only if mu is integral. That is, there is H such that this mu represents certain character as a unitary character on the group G mu. Of course, this H, we must use certain H because the kernel of mu and S mu is of course the same. So on the other hand, the integral elements in the coalgebra are related to the prequantization in the sense that this mu is integral if and only if the symplectic, the canonical constant Kirillov-Suryo symplectic form on the coadjoint orbit of mu is integral, so belongs to the integer class in cohomology. So this suggests certain relation between contact geometry and geometric prequantization. So just to end up, let me show briefly an example. So if I consider G action on a line bundle by vector bundle automorphism, then using this contact Marsden-Weinstein-Meyer reduction, I can reduce Sorry. I can reduce this to a new first jet bundle, namely this is similar to the case when reducing T star G by certain certain subgroup action, we obtain T star of reduced manifold. This we obtain first jet bundle of reduced line bundle. Okay, so I will not go into details. So, and I will finish with this. Thank you very much. So only literature if you are interested.
So thanks a lot. Please, questions or comments? You can either raise your electronic hand or unmute and ask a question. Right, I think, yeah, I see one hand raised. Could you just unmute yourself and ask a question?
Hello, Professor Grabowski. I'm sorry, there is some noise. Can you hear me now?
Yeah, yeah.
Okay, thank you for your talk. I think this perspective of contact manifolds as homogeneous symplectic manifolds is very useful, as you have shown on your proof of the Marsden-Weinstein reduction. But I think sometimes it's a little bit harder to apply when you have more geometric structures. For example, in the example of the extended cotangent bundle, you would like that the symplectization of this extended cotangent bundle would be a cotangent bundle, but and you can do that, but you cannot use the natural symplectization. You have to do some kind of trick by choosing a correct projection. Another very important space in physics is the extended tangent bundle, where you can do Lagrangian mechanics, or action-dependent Lagrangian mechanics, and this Herlot principle. I don't know if it is possible to do a similar symplectization and get a tangent bundle, because this is necessary to apply this perspective in the Lagrangian formalism. Are you aware of a way to do that?
So you can look at this position, contact geometric mechanics, the tool tree of triples. So this is exactly where the Lagrangian contact mechanics is developed in the spirit of Tulchiev, so including Lagrangians with a singular. This is related to, I didn't show this picture. So this is the contact analog of the Tulchiev triple, and consists of isomorphisms of double vector bundles, which are similarly contactomorphic. So each of these objects is a double vector bundle. So these structures are presented here, and a contact manifold. And this is a priori quite non-trivial relation between this. This you remember, for instance, TL cross. So L cross is a principal bundle. Sure. The tangent of this is again a principal bundle by the lift of the action. So this is the line bundle associated with this R cross principal bundle. We know there is one-to-one correspondence. So this makes sense. This is first jet of that. This A means the Atiyah algebroid of the principal bundle. So which is whose sections are invariant vector fields on the principal bundle. So again, this is a Lagrangian part of the triple, and this is, in a sense, Hamiltonian part of this triple. I have no time to express everything, but if you know the how Tulciev triple works in Lagrangian and Hamiltonian mechanics, you can have a slight imagination. But this is a very interesting diagram, even from the purely geometric point of view.
Yes, but I think if I'm not mistaken, if you start with a regular Lagrangian in the sense of contact mechanics, here you would obtain a singular Lagrangian. Is that correct on the symplectic formalism?
Not necessarily.
No,
Not
no,
necessarily.
if I
Yeah.
may intrude on this discussion. So this is exactly why I raised the hand, because I wanted to issue some warning that this Lagrangian mechanics, which comes from the diagram which is now on the screen, is a little bit different from what's present in the literature, because exactly what we said, if I start from Hamiltonian, typical mechanical Hamiltonian with some dissipation added by means of adding this additional Z variable and thinking in terms of extended cotangent bundle, typically I get a singular Lagrangian system with, if I think of this diagram, which is now on the screen. This is because, in a sense, we do Legendre transformation with all the variables, including this additional one. And what people usually do, they do partial Legendre transformation only in momenta, leaving this additional the variable aside. However, for this, of course, you need to have this structure of Cartesian product, because otherwise you cannot separate those variables. So,
Sure.
so this Lagrangian mechanics is a little bit different from what is in the literature.
Okay. I will try to look into this, but I'm concerned about if these different Lagrangian mechanics also obey the Herlot principle or something like this, because this is part of their interest in physics.
No, in a sense, what you get are the same phase equations. And then if you reduce those phase, because phase equations lie in the middle of the Tulciev triple, and the phase equations are the same. They are only generated differently. And if you then extract from phase equations equations only on trajectories, they are precisely Herlot's equations, the same.
Okay, thank you very much.
Okay, thanks a lot. Let's see whether there are other questions or comments. So you can unmute yourself, or you can raise your electronic hand. Maybe I have, again, a sort of naive question, right? With this contact reduction, what would be a good example? On the one hand, sufficiently simple, and on the other hand, something that one can appreciate, with some kind of non-trivial features. Is there some good thing that we can think about in this scheme? Or maybe better state, what's your favorite example?
But in what direction?
Oh, I like contact reduction, so contact manifold with a group action, and then whatever, symplectic lift. Well, what would be an interest for you? What are you thinking about when you feature, when you are looking at?
Actually, this is quite so this is even not published yet, so this is just in the process of studying. So we have some understanding how this procedure should look like, although examples, especially the examples which have strong motivation in physics, are not elaborated sufficiently. So of course, this example where you reduce the first jet bundle to the first jet bundle of the reduced line bundle is one natural, but this is the simplest possible one. You see, because maybe I, so because you see, this is the reduction where mu is 0, which is the simplest possible case, because in this situation, this standard submanifold of Marsden and Weinstein is automatically R cross subbundle, yeah, because you can multiply by reals as you want, and this subgroup which I required to be closed is just the full group. So this is just nothing but the standard Marsden-Weinstein reduction, which is applied to the case when the symplectic structure is homogeneous. But this is nothing but the standard. So in this case, this is just, so this shows how nice this approach by symplectic structure is, because I got a contact reduction just using the standard symplectic reduction with 0. Of course, if mu is non-zero, the situation, even in the cotangent bundle case, is more complicated in general. This yeah, so the as reduced submanifolds, you get again certain bundles with fibers being coadjoint orbits, things like that. So, but we didn't work on it too much to have full understanding what's going.
Okay, thank you. More questions or comments? If not, let's thank Janusz again for a great talk. Thanks a lot.
Thank you.
Yeah, so thank you everybody for coming. We're going to have another talk in 2 weeks from now. So we'll send you an announcement, and probably, right, Nikita, we can send the full list of talks that we know about, just for completeness, for better information.
It's also available on the website. So yeah, and the email contains the link to the website, so everyone can check it.
Okay, look, thanks a lot, and see you in 2 weeks from now on Global Poisson. Bye-bye. Thank you. Thank you.
Bye.